going to introduce our first presenter. It's Rajiv Asati. The name of his paper is Winning the Game War, Assuring Video Game Experience Across Multiple Domains. Rajiv Asati is a seasoned technology executive and designated as a CTO in Cisco's Customer Experience Organization. With global strategic and deep industry experience focused on digital transformation, he has incubated several cross-architectural and cross-technological solutions with specific outcomes and trusted advisory. He served on an advisory board of an IoT startup and is an innovator with more than 100 patents, over 15 IETF RFCs, and 1 CableLabs specification. Please join me in welcoming Rajiv.
All right, everybody's awake? Hi, so how many of you have Netflix? Who do you think Netflix competes the most with? Cable, HBO, ESPN? Raise your hands if you think that's the case. Amazon? You'd be surprised to recognize the fact that Netflix, in their own words, say we compete and lose to gaming such as Fortnite more than anything else like HBO. And it's a fact that more people watch gaming content, gaming related videos online than Netflix, Hulu, ESPN, HBO all combined. Now, the gamers, those who play video games, they tend to believe the lag, the latency, is what that defines the quality of experience as they tend to play. We believe there's more to it. So in this paper and presentation, we actually dig deeper and tend to look at the end-to-end view that could be beneficial for cable operators to tap into this growing gaming market. So how big is the gaming, the online video gaming? Well, it's one of the largest entertainment businesses on there, as compared to that of TV, music, and anything else. $150 billion expected this year, $150 billion. Nearly $200 billion by 2022. So it's a huge game, it's pretty big. And just to put that in perspective, if you're being exposed to the video content streaming, the CDNs, that's close to $10 billion, $12 billion expected this year. So less than 10% of the TAM the gaming industry is really bringing into the equation. And there are two countries, the gamers out of two countries who really get the majority, more than 50% of this TAM, US and China. More than 50% of the TAM. Now, there are different types of games. How many of you play games in this room? Oh, come on, admit, you play. It's not just teenagers. 2/3 of the adults in the US actually play video games. 2/3. Now, different types, so action, adventure, strategy, and so forth. And each of these types have subtypes. Like within the action, you could have first-person shooter game, third-person shooter game, and so forth. The little bit of a survey tip on the bottom right of the slide caught my attention that said, most of the gamers feel that the video game plays have a positive impact on their lives. That's debatable. But what's not debatable is that gaming traffic's impact on the network. That can be dramatic, depending on the type of games, depending on whether the game's being played or downloaded or just viewed. So let me run through that. Most of the games, it's a growing trend, most of the games now get sold and downloaded online before you can even start playing games. Those who have been doing it, 2/3 of you, know that pretty well. And put that in perspective, how big these games get just to download the initial version. Right, so Apple iOS 13 just came out. Anybody knows what the size was? Roughly 2 GB. Windows 10, when it came out, roughly 4 GB. If you're watching a 4K movie on Netflix, that's 7 GB an hour. Games, these can be as big as 100 gigabytes. 100 gigabytes. And it's pretty common. So you got to take a step back and think, well, what does that mean for the network, for my network? Right? So not only I need to think about providing faster downloads of the data bandwidth to my gaming customers, but what if there are like 50 users, right? Not many, just 50 in a given network domain. So think of a given service group, a neighborhood, just 50 of them downloading a game. You know what would that be if they were downloading Call of Duty? That's 5 terabyte worth of traffic going through that access domain or that network domain. That's quite a bit of stress. And that's, of course, predominantly in the downstream direction. Now, 50 users is just an arbitrary number. Depending on a neighborhood and the population, there could be 500, 5,000 users that connect into a single CMTS. Think about the impact that could have. Oh, by the way, these games tend to have patches, right? The new updates. That could actually be in 3 to 4 to 6 to 10 gigabyte. And in order for one to play the next game, well, you got to get the patch applied. So that really adds up pretty quickly. So once you've downloaded the game, you got to play, right? So once you start playing, it's important for us to recognize the characteristic of the gaming traffic, the actual gaming traffic. Because then we can relate to what the network needs to have, what the network needs to be able to offer and be able to accommodate. So gaming traffic mostly is UDP traffic, right? The big internet is now moving towards UDP, as many of you know. The internet is no longer about TCP. It's predominantly, or becoming very quickly predominantly UDP based. Well, gaming from the get-go had been based on the UDP. And the packet sizes were relatively small, and to this day, depending on the game, you could see in the upstream direction, the packet size is as small as 50 bytes. You know why? Because when somebody hits a keystroke on a controller or on a computer, that keystroke has to be sent from a client to server. Remember, it's a client-server architecture. What that means, hub and spoke traffic. So the message has to go from client to server and come back. So that, in the upstream direction, is a very small packet size, usually 50 to 100. In fact, 90% of the traffic in the upstream direction tends to be 100 byte or less. In the downstream direction, the packet sizes get relatively bigger. And what we have seen is that 90% or more of the downstream traffic could be less than 500 bytes, though we have seen spikes going up to 900 bytes or so. Now, that varies from game to game, so that's just one representation. But what's important to recognize that these games involve the packet rate that's relatively higher than what the other types of traffic the network may have. And the packets per second becomes a very important characteristic. So how frequently the server is able to send a snapshot to each and every client dictates a packet rate. So anywhere from 30 packets per second to 150 packets per second, and that's really high. And that, again, is a function of the snapshot rate and the tick rate that the games would have. Most of these games tend to be CBR, like constant bitrate. So these packets get generated at every few milliseconds. Could be 15 milliseconds, could be 10 milliseconds, could be 5 milliseconds from the server that get updated to all the clients. So, and these are usually long-lived flow. It's not like you're watching one YouTube stream, 5 minutes over, done, flow is gone, killed. Now these games, these could last not only for 30, 40 minutes, but hours. Those who have been playing games, you know how deep you go into the wee hours of every morning, right? No, nobody does that? Yeah, there we go. Now also, recognize the fact that in terms of the downstream to upstream ratio, in a multiplayer game, more the players, higher that ratio. It's almost proportional to it. So what that means for the network, when you start thinking about the policies, you got to have those UDP-based policies, not just TCP-based policy. If you need to accommodate for any specific conditioning for this gaming traffic. When you choose a platform in the network, it has to be not just bits per second throughput oriented, but also for packets per second oriented. As more and more gaming traffic comes along, more and more PPS capacity would be needed out of the networking devices. And one of the most important characteristic in there is the latency, right? The CBR-like flow. Well, CBR-like flow, that means in order to ensure that we honor that characteristic of the game, you gotta be able to put some quality of service constraint to it. Now, these characteristics are what we know of, largely not what cloud gaming could offer. We'll have a bit of a discussion on cloud gaming later in this presentation. So the cloud gaming, which heavily tend to rely on streaming, not just for download, for upload as well, they could have a much bigger packet sizes, could be a lot higher packet rate and combination thereof. And there's a thing called lag, right? Many of the gamers, they complain about the lag. I got too much lag. And what is really surprising that ubiquitously within the gaming community, the lag is measured with latency that most of us in the networking realm know. They measure that lag in terms of ping time. And the first rule of thumb in any architect or strategists or designers in the networking realm is to not equate ping time as a reflection of latency, right? But this is what it is in the gaming world. What we believe is the lag really is defining more of a quality of experience for the gamers. I mean, which is really depending on not just the latency, but also the jitter, which is one of the worst things to have in a gaming to impact quality of experience on drops and so forth. Look at the picture on the bottom right side where a player is taking a shot at a target, right, which is moving. So when the player takes a shot, it hits a keystroke, that command has to go to the server. Now the server, without doing anything fancy, would declare that the shot which was taken perfectly actually missed the target. You know why? Because by the time that packet went from client to the server, the gaming world had changed, meaning the position of other players had changed in that time duration. So if the latency is 40 millisecond or 80 millisecond or 20 millisecond for that gamer versus the target's latency, well, the target would have moved by the time server starts to process it. So a lot of these games employ what's called lag compensation algorithms, LCAs, so that they can counter against the impact of the latency. Gamer 1 may have 20 millisecond, gamer 2 may have 40 millisecond, gamer 3 may have 80 millisecond. They gotta figure out a way to keep the gaming context intact. So what would they do is that the server side logic would actually keep the trend and the history of 100 to 200 millisecond of every player's position. And they can rewind by the time that player had, when it issued the keystroke, the latency that it took, the server would go back, detect the latency time, and says where each and every players were at that time. And would say, now if I were to take a shot, from this gamer's point of view, would it take a hit? And if the answer is yes, even if the player's position have changed, their server would say, yep, that's a hit. And that's when all other clients, the gaming clients, would see that update, yep, this was a hit. And that's what the blue and red are conveying, by the way. Blue being at time t1, red at time t2, based on what server would have thought. So far so good, right? So there's the gaming engines, there are many of them out there, the open source and not gaming engines. They have these lag compensation algorithm among many other different fancy machine learning based algorithms. But they struggle to cope up with the changes in latency, meaning jitter. So if the latency that the clients continue to convey, hey, I'm 30 millisecond, and then server is using that number to calculate the prediction output, and all of a sudden the latency goes from 30 millisecond to 80, guess what? The whole prediction model that the service would have would not be right anymore. And well, many of you may know the latency, forget the internet side, just inside the MSO network can just go haywire. And that goes beyond DOCSIS. Sometimes just routing, just in this, in one of the states, earlier this year, I got exposed to an issue where the latency jumped from 20 millisecond to 68 millisecond. And it wasn't a one-time thing. It's like happens at different times of the day, times of the week. If you know it's your network, don't tell this to anybody. So what's a good latency? Well, 30 millisecond or less is perceived to be really good latency from your gaming customer's point of view. And what that means from the network point of view, you gotta ensure that you have the deterministic SLAs in place, especially for latency, to provide the better gaming quality of experience. While you're playing it, well, there's another thing called game viewing, game watching. It's huge. It's the second most popular on the internet. Second most simultaneous viewing on the internet. Why? Because many of the gamers love to broadcast their games in high def or ultra high def. So imagine what would happen if just 1,000 users in your 1S, G, in the service group SG, or in the neighborhood watching that game in high def. Just 1,000. That's 5 Gbps worth of traffic. What if they're watching in ultra high def, 4K? That's 25 Gbps. That's quite a bit of stress on the network. Now couple that with the fact that there may be 10 users playing the game, just 10 users playing the game in the same service group, and 50 users downloading the game. What would that do to that network domain? What would that do to the quality of experience the gamers would have? Right, so clearly expect the downstream usage to continue to increase because of the gaming, not just because of download and gaming play, but also because of viewing. And also expect the upstream traffic usage to grow as more and more gamers like to broadcast their games. Now, if you think about all that and put that in perspective of what the network domains could be, right, starting from the home network to access the HFC, the cable DOCSIS, then to aggregation, the hubs and the backbones, to the internet peerings and to the data center where the games get hosted, each of these domains have a unique role to play. Some more, some less. Some are in the direct control of you, some are not. So in the paper, we actually drill down into each specific domain and make recommendations. In the interest of time, I would only talk about the 3 of those domains that would be pertinent. Right? So the home network, preferred wired connectivity to Wi-Fi. Now, it's easier said than done. I know many of my friends actually just stick with Wi-Fi because where the junction is, where the gaming console is, and so on and so forth. So the wireless, of course, continues to grow. So the key is to focus on having 802.11ac or AX, the latest Wi-Fi 6 in place, because Wi-Fi 6 actually does have a lot better modes for controlling quality of service. 5 gigahertz or higher. Right? That's really, really important. If there is no blockage, meaning there's a reasonably clear line of sight. And the thing that is really fascinating from innovation point of view is this dual channel Wi-Fi, where the upstream channel is different from the downstream channel in Wi-Fi. And this is not common. Almost all homes, home routers, Wi-Fi access points do not have this. Even most of the sophisticated ones do not have that. So it's an upcoming innovation that's going to be really, really important to embrace and to spur the usage of Wi-Fi with the quality of experience for gaming. But the better one and more pertinent one here is the access network, right? Now, drops and mentions, right? How often do we have drops in the cable plan? So gotta keep the cable plan pretty clean. Be able to leverage the DOCSIS innovation like low latency that Greg's gonna talk about the next, to be able to keep the latency and jitter well contained, right? Now, what's the magical number? Well, there's no magical number in here, but keeping the latency well contained within a range, so 10 millisecond doesn't jump to 40 millisecond and vice versa, that's going to be important. congestion reduction, right? So by having mains to either split the nodes or really increasing the overall data rate is going to be very key to allow the gamers to be able to stream or download the game at a relatively faster pace. But that's one part of the bigger puzzle. The other bigger part of the puzzle really is on the peering side. Many gaming companies have started to build their own network and started to build their own network with peerings that would get closer to the ISP networks. Why? Because if the path between the client and the gaming server is indeterministic, that adds on to the overall latency and the drops and the jitter. So, better the peering points are, if you can reduce the number of hops between the gaming server and the gaming client as a cable MSO, you have much better control over the gaming quality of experience of your customers. Now, there is also a possibility to actually have gaming exchange points. Right? How often you have been exposed and being involved in dealing with IXCs, Internet Exchange Centers, Internet Exchange Points? There is no such thing as gaming exchange points, which is what's causing a lot of problems. And there are companies like WTF, which actually have spurred up to say, hey, we're going to figure out a way to cut down the number of hops between the ISP network and the gaming center. And there could be 3 other ASNs in between. That's a big variation in the overall equation as well. So going beyond that, then what else we could do, right? Remember, the first thing the customer who has an issue, the customer does, calls the ISP, the cable company. Right? Now, so the MSO have an opportunity here to partner with the gaming providers and really have ability to put some hooks into the games. And as far-fetched you might think this could be, it's really not. There are few niche players in the industry that are sort of sitting as an overlay and including and inserting their own hooks, their SDKs in actual games. And that allows them to collect a lot of data points, which in turn allows them to steer the traffic over a network A versus network B. So the cable MSOs clearly could go beyond that, right? Could not only be able to put hooks, but even couple things such as packet cable, multimedia, machinery, and allow for the gaming traffic to be prioritized even better. Right? So having a better assurance construct can really set up cable MSOs to be able to do a lot more. Also be able to host gaming server, right? So gaming servers today are scattered across the internet. Well, there may be one on the West Coast and maybe one on the East Coast, if you're lucky, and that's it. And your customers are all over the US. And you have fantastic set of data centers, both centralized and distributed with edge clouds or not, that could be taken advantage of. Right? So there's a lot of really interesting play from the gaming perspective that MSOs can employ. Now, cloud gaming is another fascinating thing. The Google Stadia is supposed to be launched, I believe, next month? Friday. Thank you. You're keeping up pretty well with that. Well, you know what that means? That means more stress on the network. More stress on the network. And in fact, 2 times more. So if you compare that with 4K video viewing, right, 7 gigabyte per hour on one side and Google Stadia, if you're playing that game in 4K, if you have customers who are playing that game in 4K, that's 15 gigabyte per hour. So come Friday, more and more games get added over the next few months. More and more of your customers join. Guess what's going to happen to the network? So the cloud gaming really is intending to disrupt the gaming industry big time. But what the impact that's going to create on MSO network is clearly more load on the network that needs to be dealt with. So I want to summarize my presentation by conveying the fact that video gaming is one of the largest businesses on the internet. And it's growing exponentially. Now, quality of experience for gaming customers is a multi-domain puzzle. is multi-domain, which cable MSOs can really fine-tune across at least 3 of those domains, perhaps 4 and all 5. And remember, lag is not necessarily latency only. There are multiple of these things, recommendations that we have outlined for MSOs to do more. For example, bandwidth reservations for gaming service flows, if you're able to recognize and classify that kind of traffic. DOCSIS innovations are really key. So latency, low latency DOCSIS as an example, or FDX, those are really going to be foundational to ensure the gaming quality of experience for your customers. With that, thank you.
Right, thank you, Rajiv. Very insightful. I find it pretty compelling that the bandwidth models are changing, right? Basically, it's no longer about videos and movies versus the web. It's about gaming versus it. So, very interesting. All right. So, without further ado, the colloquial term for latency. There's not many latency jokes I can make. I'm going to introduce Greg White, whose paper is Low Latency DOCSIS, Overview and Performance. The summary on this is that low latency DOCSIS makes the internet experience better for latency sensitive applications without any negative impact on other applications. Greg's going to dig into the underpinnings of why that's true and what it takes to make that happen. Let's do this. Oh, actually, I just want to introduce Greg. Sorry, 1 second here. For those of you that don't know, Greg's been around a long time, but for those of you that don't know Greg, he's a distinguished technologist at CableLabs. He's been an integral part of the DOCSIS program for many years, including leading the DOCSIS 2.0 and DOCSIS 3.0 specification teams, and leading work on reducing DOCSIS latency via buffer control and active queue management. He's currently leading the low latency DOCSIS project at CableLabs and related standardization efforts at the IETF. Please join me in welcoming Greg.
All right, thanks, Joe. And thanks, Rajiv, for that introductory material. It kind of helps set the stage for the importance of latency going forward in cable networks. So I have this slide of why low latency DOCSIS. And maybe the high-level answer is everything that Rajiv just talked about, that latency is important for games, and maybe it doesn't exactly equal the same thing as lag from the perspective of the user, but it's a significant component of that, and a significant component of the user experience. This is a measurement that we did on a North American ISP's network. And this is measuring round-trip time from a client device to the interconnect. So this is traffic that was exiting the ISP's network, and so measuring end-to-end across the ISP's network. Median latency, not so bad, 18 milliseconds. But when you start to look at the tail distribution, 99th percentile, 200 milliseconds. 99.9th percentile, 1 second of latency round-trip. And you might be thinking, well, 99.9th percentile, that's kind of way off in the tail of the distribution. Who really cares about those kind of statistics? Well, if you're thinking about an online game which is sending packets at, say, 60 packets per second, a 99.9th percentile event happens on average once every 16 seconds. So these are definitely experiences or events that are affecting the experience of gamers on cable networks. And this is measuring more than just the DOCSIS link. It's measuring Wi-Fi in some cases. It's measuring the core network as well. So how much of that comes from DOCSIS? Well, the table on the lower right there illustrates, the answer is it depends. It depends on what is the scenario under which you're measuring latency. Is it when the link is totally idle, when the customer's not using the service, and they just do a ping test to see, ping the CMTS, for example. So that's kind of the when idle state. Under load would be when they're actively using the connection. So maybe there's other users in the household that are streaming video or downloading files, downloading a massive file download for one of these games. And the 99th percentile is sort of a measure, again, towards the tail end of the distribution of things that, events that happen often enough to really impact the user experience. And it also depends on what version of DOCSIS you're talking about. So the different rows in the table summarize kind of the evolution of performance of different versions of DOCSIS. And you can see that over the years we have made improvements on some of those metrics. On the bottom, low latency DOCSIS 3.1 achieving a millisecond round trip across the DOCSIS link under all those situations. And up to the top left, the goals of the project were really to be able to achieve that 1 millisecond at 99th percentile. So we provide a consistent experience for the user. And then not just focus on that one kind of stripe across the CDF plot, but also look at median latency and making sure that we're not making things worse in other parts of the distribution. And do it in a way that we're not throwing away something else. So we're not doing it and reducing TCP bulk data throughput. So we get good performance with bulk data as well. And then on the bottom of that upper left, design this in a way that makes it easy for operators to deploy. So it can kind of just work and not a lot of knobs to fiddle with to make it work well. But provide some knobs in case there are some specific use cases that need some customized configuration. All right. So what's causing all this latency historically in the cable access network? So in DOCSIS 3.1 as it is today, we broke out what are the sources of latency. In this bar graph, the length of the bar represents the range of latencies that could occur as things, in common network environments. So queuing delay, the number one. It can be 0 in the case that the customer service is totally idle and they do that ping test. There's no queuing delay. A packet arrives at the cable modem, goes straight onto the upstream channel. But it can be as much as 200 milliseconds. Even with some of the features that we added initially in DOCSIS 3.1, the active queue management feature, which you may be familiar with, you can still see spikes of latency that get up into the hundreds of milliseconds. Media acquisition, second one on the list, that's the DOCSIS protocol where when a packet, that's how a packet gets onto the upstream channel in DOCSIS. Right? A modem receives a packet, the modem has to send a request to the CMTS, and then it waits for a map message to come back, and then it waits for its transmission slot that it was told about in the map message, and then finally it gets to send the packet. That can range on the order of 2 to 8 milliseconds typically. Serialization and encoding, that's all the channel parameters that cable operators have to work with. The modulation and interleaving, forward error correction, all those different functionalities can range anywhere from 400 microseconds up to about 3.5 milliseconds. Propagation delay, that's just the speed of light and distance, so not a whole lot we can do about that one. And switching and forwarding is a pretty small number, but that's just the decision making within the CM and the CMTS about forwarding traffic. So in low latency DOCSIS, we tackle the top 2 line items here, queuing delay and media acquisition delay. And there are 2 components, 2 fundamental components of the technology that address those. Dual queue is a mechanism which addresses that queuing delay. And it has a number of subcomponents, and I'll get into those in the next few slides. And then upstream scheduling, there's improvements there. That's to address that media acquisition delay. And again, it has a couple of components, which I'll talk about. All right. So what's causing this queuing delay? So that was that huge bar at the top of the slide, a couple of slides back. What causes that? So network elements in an IP network have to support some kind of a buffer that can absorb bursts of packets that arrive, and particularly in the case of a bottleneck link. So bottleneck link being one where the egress link is a lower rate than the ingress link, or maybe it's multiple ingress links coming in and sharing an egress link. And so that buffer becomes very important for absorbing bursts of traffic that arrive at a rate that's higher than the egress can support, and those packets stack up in a buffer and then get played out on the egress link as quickly as they can. And it turns out that the transport layer protocols, the layer 4 protocols, have been designed to take advantage of that buffer, to assume that there's a buffer in place and make use of it. And so all of the congestion control algorithms that are used in TCP and QUIC and WebRTC take advantage of that queue. And in fact, a lot of them tend to keep that queue full, keep that buffer full, which then causes latency, right? So if you've got a buffer that can hold maybe 200 milliseconds of traffic playing out on the egress link, when that's full and a packet arrives from another application, it's waiting 200 milliseconds inside that network element before it gets out onto the wire. So that's queuing delay. The realization we had when we were designing, starting off designing low latency DOCSIS was that there are a lot of applications that do that are filling up that buffer, and they're keeping it full as they try to saturate the link with traffic, try to sense the capacity of the channel. We call those queue building applications. But there are also a lot of applications that don't do that. They're just sending traffic at the rate they send it. Maybe it's the 60 packets per second of a game, or maybe it's 100 packets per second of a voice call. They're not trying to seek the capacity. They're not trying to fill the pipe with data. They're just trying to send it at the rate they send it. So we call those non-queue building applications. And if we can identify the non-queue building applications, we can then separate them and segregate them from the queue building applications. Give each category its own queue in the network, both in the CM and the CMTS, and let those non-queue building applications effectively bypass the delay caused by the queue building applications. So how do we identify them? It turns out there's really two subclasses of these non-queue building applications. One of them are these fairly low data rate applications, and again, online gaming is a good example of that, voice over IP. These, we're standardizing a diff-serve code point that the sender can use to mark its packets as non-queue building, and then the network can identify that code point in the packet and map that packet into the queue for non-queue building applications. The second category are future applications that would like to be able to ramp up to the full channel capacity, be able to sense the capacity of the channel and fully utilize it. But they also want to do that and maintain ultra-low latency, ultra-low queuing delay. Turns out there is a solution for that as well. It's called L4S, and low latency DOCSIS supports L4S. I'll get into what exactly that means in a little bit. But some examples of applications, some near-term applications that would, again, want to be able to scale up to high throughput and do that with ultra-low latency. Cloud gaming that Rajiv just talked about, Stadia, Microsoft xCloud, NVIDIA's GeForce Now, things like that that are coming on the market very soon, or some of them already are available in beta that are, again, a great example of this type of application. Pause for a second on the technology and talk about net neutrality for just a second. So we're going to talk about segregating traffic into these two queues. You might be thinking, oh, I've heard this before, so you're just identifying the latency-sensitive traffic and giving it high priority. Yeah, I've heard that before. That's not what we're doing here. Think back to what that slide said. It wasn't segregating latency-sensitive from latency-insensitive traffic, and it wasn't segregating high-priority traffic from low-priority traffic. This is solely based on the application behavior. Is it queue building? Is it causing latency in the network by the virtue of its behavior, or is it not doing that? So segregating solely based on application behavior. And when we talk about how that maps into network neutrality, one of the key points is this isn't a zero-sum game. We're not making latency better for these non-queue building flows and making performance worse for the queue building flows. It's not a good queue and a bad queue, or a high priority queue and a low priority queue. They're just two good queues, but just optimized for these two different application behaviors. A deep buffer for those queue building flows that need to have a deep buffer to get good performance, and a short queue for those non-queue building flows that don't want to suffer the latency and loss that's caused by TCP and QUIC and things like that. Second point is, by default, it's up to the application to mark its packets. So we are letting the application make the decision which queue it would do better in. Is it a queue building flow? Does it need to have that big buffer and make use of that? Or would it do better in a non-queue building buffer? And then finally, every application could be non-queue building if it wanted to be. Using the L4S technology, which again I'll talk about in a couple of minutes, even bulk data flows, if they wanted to, they can adopt L4S and be non-queue building and get ultra-low latency as well. All right, so let me jump into the details of the technology, how this all maps into the DOCSIS technology. So, if you're familiar with the concept of service flows in DOCSIS, this will look somewhat familiar. The dual queue mechanism, again, this is two queues in the upstream direction in the cable modem and 2 queues in the downstream direction in the CMTS for the user. Those are instantiated as 2 separate service flows, a low latency service flow and what we call a classic service flow. Low latency, as you probably have figured out, is for the non-queue building flows, and the classic is for the queue building flows. And then we wrap that in what we call an aggregate service flow, and that's where the rate shaping takes place. So the customer's service level is defined by the rate shaping that's applied to that aggregate service flow. That way, if all the traffic happens to be in the low latency service flow, the customer's traffic can achieve this the service rate, or if it's all in the classic, it can achieve the service rate, or there's a mix of traffic in both service flows, it can share that aggregate service flow capacity. Then there are classifiers. Classifiers are a fundamental part of DOCSIS and how traffic gets mapped onto service flows. We use that same technology here, but we instantiate some default classifiers for this specific purpose of identifying the non-queue building flows using that diff-serve code point or the packet marking that the L4S mechanism defines. Now you may be thinking, okay, so we're trusting the application to mark its packets as non-queue building and get low latency. What happens when everything marks its packets as low latency? What happens then? Well, we have a function we call queue protection that protects the latency of the low latency service flow. So I guess the first point would be there's no incentive for a queue building flow to mismark its packets as non-queue building. It would just end up in that short buffer and getting worse performance. So it's in its best interest to not mismark its traffic. But bad things can happen, or you could have a malicious application that is trying to flood traffic into the low latency service flow and marking itself as non-queue building. So this queue protection function is monitoring all of the flows that enter, that are classified to enter the low latency service flow. It's also monitoring the queuing delay in that service flow. And if the queuing delay starts to grow, it identifies the application flows that are causing it and redirects the packets of those flows to the classic service flow. So a little bit of a trust but verify. All right, coupled AQM. So this is the mechanism that supports the L4S architecture. So L4S stands for low latency, low loss, scalable, and it's a new congestion controller for TCP or UDP or QUIC that allows a connection to scale up rapidly to the channel capacity and do that in a way that doesn't cause latency and loss. And the way it can coexist with existing classic TCP flows. And the way it coexists is through this coupled AQM mechanism. If you're familiar with AQM, AQM stands for Active Queue Management. It is a mechanism where a network element monitors the queuing delay inside of a queue and then sends congestion signals via either packet drops or ECN marks, explicit congestion notification marks on packets, to send the signal to the sender that needs to slow down. In this coupled AQM, there is an active queue management that's running on the classic service flow. It's the DOCSIS PI algorithm that was defined as part of DOCSIS 3.1. And then the low latency service flow has a new immediate AQM algorithm that's running there and sending signals to L4S flows that are in that service flow. And then the coupling mechanism between these two AQM algorithms ensures that a consistent congestion signal is sent to both categories of flows so that they can all compete fairly for access to the channel, all get fair access to the channel. All right. So L4S, again, low latency, low loss, scalable. A new congestion controller for TCP, QUIC, and UDP. The scale part of that is it solves the scalability problem that TCP has today. If you do a speed test today, you can't just do a single file transfer and saturate a broadband connection reliably. You have to do kind of a multi-threaded test where you're sending 4 or 8 or sometimes 16 simultaneous TCP flows in order to fully saturate the path. L4S solves that, so it's scalable up to multi-gigabit per second connections. And it also solves the TCP buffering problems, where TCP causes this buffer in the bottleneck link to be full and causing delay. and as I mentioned, it can coexist with the classic TCP using that dual queue coupled EQM. All right, so that was all the dual queue mechanism that supports eliminating the effect that queuing delay has on those non-queue building applications. The next piece is talking about the media access control aspect. So again, that was that 4 to 8 milliseconds of latency on the upstream caused by the request grant cycle. There are a couple of features there that we added in Low Latency DOCSIS to address that. One of them is really just kind of putting a stake in the ground in terms of performance in the CMTS around the scheduler function for responding to requests. The specs prior to this point had no requirements around that, and so we chose requirements that the CMTS has to support a 1 millisecond map interval, so that's the unit of time that it schedules on the upstream channel, and it has to turn around the scheduling information in 400 microseconds or less. Fairly straightforward on that one. The second one, maybe more interesting, is a new scheduling type for the upstream channel called PGS, or Proactive Grant Service. If you're familiar with these upstream scheduling types in DOCSIS today, best effort, real-time polling, UGS, UGS-AD, that kind of thing, you can kind of think of PGS in a sense as a hybrid between the best effort scheduling service and the UGS-AD scheduling service. It's not exactly that, there's a little bit more to it, but that's kind of a good starting point for understanding how PGS works. I'm not going to go into all the details on this slide, but there are 3 parameters that the operator can set in order to configure the PGS service. All right. Some of the components of this architecture are being standardized not only within the cable industry in DOCSIS, but also in the IETF because they affect the end-to-end application behavior on the internet. One piece is this L4S architecture. It's not a cable-specific technology. It really could be adopted by any network technology. There are 3 drafts there. They're working their way through IETF. And then finally, for that non-queue building code point for applications that are the low data rate applications to use to mark their traffic as non-queue building, we're standardizing a code point for that. All right. Let me get into now, so the technology, how it all kind of fits together and how it works. I'm going to get into some of the expected performance that we expect to see in equipment when it becomes available. This is all based on simulation at this point because we don't have equipment that implements low latency DOCSIS yet, although it's coming. We'll go into really 5 scenarios that you'll see in a couple of slides, looking at kind of adding in those low latency DOCSIS features as we go. So when we run these simulations, we have to have some model of real user behavior to load up the channel with different applications that, in particular, TCP applications that are causing queuing delay, right? So we have a set of traffic mixes that we've been using to try to model residential broadband use, kind of prime time use. Some of them are heavier load than others. And then we look at the 99th percentile latency. So this is simulation results. You see the rows are the different traffic mixes, and the columns are these different scenarios. First starting off with your DOCSIS 3.1, if you turned off AQM or didn't have it enabled in your network, 200 milliseconds at 99th percentile for that. Add in AQM, that drops you down to 68 milliseconds. Lower the map interval from 2 milliseconds down to 1, and that shaves off actually 4 milliseconds at 99th percentile. And then you start to get into the real low latency DOCSIS features of the dual queue functionality, dropping that 64 down to 4.7 milliseconds. And look at the column above that. In the previous 3 columns, you saw radically different numbers depending on what the user traffic pattern looked like. Right, it could range from 4.5 milliseconds up to 180 milliseconds or more. With low latency DOCSIS, it's kind of rock solid at 4.7, 4.8 milliseconds across all of those traffic mixes. And then if you add the PGS scheduler to the mix, that can drop you down to that sub-millisecond queuing delay at 99th percentile round trip across the DOCSIS link. Well, I circled the 4.7 milliseconds because PGS comes at a cost. It comes at a cost of some wasted bandwidth on the upstream channel, some wasted capacity. And so for a mass market service out to a large population, probably that PGS may not be the right technology to use. So maybe that 4.7 milliseconds number is a more realistic for a mass market service. This slide goes into just a little bit of that interaction between the PGS overhead and the latency. So you can see as you scale up the amount of capacity that you're dedicating for a customer for using the PGS scheduler, you can bring that latency down from that 4.7, 4.8 milliseconds down to the sub-millisecond number. And kind of hit diminishing returns at around 3 megabits per second. But that's 3 megabits per second of capacity that you're dedicating to that low latency service flow for that customer. And so that could be on each customer. All right, and to wrap it up, where these functions sit in CM versus CMTS and thinking about equipment and deployment of the functionality, all the downstream features, all the dual queue functionality in the CMTS is just in the CMTS. There's nothing that the modem has to do to take advantage of that dual queue functionality. And so as soon as the CMTS supports low latency DOCSIS and supports the downstream functionality, you can roll it out to all of the cable modems on the plant. So they don't have to know anything about low latency DOCSIS. They could be DOCSIS 3.0 modems, they could be DOCSIS 2.0 modems on the network. The upstream side, unfortunately the reverse is not true. The upstream features do require both the CM and the CMTS to support them in order to turn those features on. But we did add some nice provisioning tools that allow an operator to configure the service so as soon as the modem gets a firmware upgrade and can support the low latency DOCSIS features, they automatically get instantiated and the service is being provided. All right, so that's all I had for slides. We just had an interop on low latency DOCSIS last week. We had multiple vendors participating, one CMTS vendor and both of the modem silicon vendors participating. A great first interop. We ran through a number of the test cases looking at the registration process, making sure the CM and CMTS are exchanging all the information they need to bring up the service. The immediate AQM, we tested that. Queue protection, we tested that. And the PGS scheduler. And found some bugs, fixed some bugs, and found some more bugs. So things are not done yet by any means, but it was a good first interop and a good start. So thank you.
Thank you, Greg. I feel like you just scratched the surface of all the material you could have covered, and that would easily take a few hours. We're going to open the floor to questions that you may have. So if there's anybody who'd like to speak up, just raise your hand. I was taking some notes from this, and as I've gone over the material with Greg and Rajiv, I still keep on coming up with more questions. So who's got? Go ahead.
I have a question. Regarding the neutrality, understood your point, but even if I have a new source and I mark as a new source is a better part of experience for gamers, it's still be an issue for neutrality.
Yeah, so for those in the back who may not have heard, the question was about offering low latency DOCSIS as a service that maybe is marketed towards gamers, and does that have implications on, I guess, views around network neutrality? Does it sound like it's prioritized traffic? Yeah, that's definitely a concern. You know, as this technology gets rolled out, the messaging is going to be key to make sure that we're telling the story of the technology and how it works, and not making it easy for misinterpretations to take place. I think that's definitely a risk that we all have to consider, especially as operators need to consider as they market the technology and discuss, you know, the functionality and how it works.
And I'll also add one more thing, right? So differentiation across different types of traffic may not be such a big concern, but what could be concern is that one type of gaming traffic gets prioritized, another type of gaming traffic doesn't get prioritized because of whatever relationship that might have. That would be a concern, but just prioritizing all types of gaming traffic for the benefit of the cable MSO's customer should not raise any concern from net neutrality point of view.
So in terms of a hacker that is intending to do a denial of low latency service to a customer, the queue protection function is intended to mitigate that, right? So it can identify flows that are causing latency to build up in the low latency queue and redirect the traffic to the classic queue. So it's protecting the latency in that queue. So that's a pretty strong functionality that can help prevent misuse or malicious actors.
In the back?
Yeah, a couple of things I could say there. There's a lot that you can. A lot of the latency in video streaming comes with the HTTP-based delivery, right, and the chunk sizes, and the playback buffer that the client implements, and those typically are on the level of seconds, right? 5-second or 10-second chunks of video, and Netflix, I think by default has like a 3-minute playback buffer. So there's a lot that you can do, maybe low-hanging fruit there. Low latency DOCSIS, where we're talking about reducing spikes of 200 milliseconds down to 0. It's a different scale, but the L4S functionality, the scalable aspect of the L4S, I think could definitely be helpful for streaming video, allowing it to ramp up to channel capacity very quickly and fully make use of the channel. Right.
I guess my question was more, we're looking for Netflix and gaming is going. There wasn't really anything about where the OTT was going. It is seconds today, but they're trying to get that down. Ultimately, you're going to have much harder requests for video packets and need them very quickly if you want to maintain a sub-1 second.
Right. Yeah, and the cloud gaming companies are really blazing the trail there because they're encoding video, right? A cloud game, what it is the game console or PC effectively is in the cloud. It's running the game and it's encoding the video using a VP9 or H.264 codec, and then delivering a video stream to the user. And then they've got a controller. Their controller stream is sending updates back to the renderer. So you need very, very low latency loop time for that to work well, right? And so that technology, Google Stadia has their own mechanism for adjusting the codec rate based on looking at inter-arrival times and estimating channel capacity. We've had detailed discussions with them about L4S and taking advantage of low latency DOCSIS, and so they'll be migrating to using the L4S marking that our technology provides in order to optimize that service. But that exact same functionality could be used for live broadcast video as well.
So we know that the applications need to mark the packets as non-queue building. Are there any applications that are doing this today?
Not really. So we're standardizing a new code point for non-queue building applications, and that code point hasn't been assigned yet. So there isn't anything that's using that specifically today. But there are applications that do use diff-serve code points, using like expedited forwarding code points. Some of the voice over IP adapters do that already. But we do have kind of a road ahead of us in evangelizing this new code point and getting application developers to start using it. We're planning on doing a presentation at GDC next year to kickstart some of that evangelization. We've talked with the game engine developers as well about taking advantage of this. There's a lot of interest, and what we hear from them is, tell us when we can start playing around with it. Tell us when we can start using it. So I think there's definitely demand for it, but it'll be some steps to get there. For sure.
Okay. Right there in the back with the gray shirt. and then we'll go up to her.
Comment on the upstream side where cable modems vendors also have to be involved in the effort as well as the CMTS vendors. So on the cable modem side, how much work, what's the size of the scope of the efforts and what are the dependencies?
Yeah. So we designed the low latency DOCSIS technology so it could be a firmware update on existing DOCSIS 3.1 equipment. So all the existing DOCSIS 3.1 modems that are out there in the field today can be field upgraded to support low latency DOCSIS. And in order to do that, we had to actually move some of the functions that might have made sense to implement in the modem, to move those into the CMTS. So it ends up that there's a fair amount really that the CMTS has to do, and there's not a whole lot on the modem side. The functionalities on the modem are that coupled AQM and the queue protection function. And then we also added some other features which I didn't talk about in the presentation, where the modem does estimates of queuing delay and it can store those in a histogram that the operator can then collect to see the statistics of latency over time. So that's another feature that.
Sorry, follow-up question. So I realize obviously it's vendor dependent, but are we talking about, is that like a 6-month effort once you come into the work? Is that like a year worth of effort for more vendors?
So the specs were released in January of this year, and we just had the first interop last week, and we saw a lot of progress made already on the modem side, silicon side. Still some work to do. We have another interop in middle of November, and then we have a couple more on the calendar for the beginning of next year. Hopefully we won't need all of those, but my expectation is that we'll have modems that are fully supporting low latency DOCSIS by first quarter of next year.
Thank you.
Second row, blue shirt, I think you had your hand up, or? Yep.
I was just
Green.
wondering, for the dedicated service flows that you talked about, do you have an example of how you built those service flows on the CTS or on the cable modem config? Do you use like a specific UDP port or?
Yeah, so for the classifier, the default classifier is to look at that diffserv field, so the specific diffserv code point that identifies NQB traffic, and then the ECN field, which identifies the L4S traffic. And so by default, those classifiers are created. We designed a few mechanisms that the operator can use to instantiate the service. One of them is, and a couple of them utilize a new table that's defined on the CMTS called an aggregate QoS profile table, AQP table. And it defines named QoS classes, just like the service class table does today. And so one mechanism you can use is take an existing DOCSIS config file. If it's defined to use service class names in the definition of the service flows, the CMTS will do a lookup in this AQP table and find the expansion of that QoS class into the two service flows and the aggregate service flow, the classifiers that go along with that, and the operator can override the classifiers in that AQP table if they want to, or just use the defaults that come along with that. Or you can do the full TLVs in the config file too. You can define everything explicitly in the config file.
Any questions from the side? Sure.
Yeah. Any other applications that you see that should be advantage of low latency or possibly high frequency trading or something like that?
Sure. Yeah. Certainly, any application, I guess, that considers latency and reducing latency variability to be important. So I guess the ones I listed, definitely gaming and voice over IP and video conferencing and things like that. High frequency trading, you always hear stories about people running their high frequency trading systems like on the floor above the exchange or something like that. So I'm not sure how big a market that is for high frequency trading at home, but sure.
The other application could be, I think, the mobility, right? So as the virtual RAN continue to gain more traction, 4G or 5G, that would definitely be one of the biggest beneficiaries. Okay.
Also, web browsing. Web browsing performance, page load time is far more sensitive now to latency than it is to throughput. Above about 6 or 10 megabits per second, you're latency bound and not capacity bound. And so reducing that latency can improve page load time as well. Web.
Was there someone in the midsection here? Yes.
Yeah.
Did you catch that?
Sorry, what was the question?
So the first one is your thoughts on the practicability of using the HFC network for fiber transport as an alternative to fiber. And then the second part of that question is, if you use it for 5G transport, the specific use case of fronthaul requires a lot lower latency than what goes there.
Yes, that's a good point. So on the first part, right, the practicality, I mean, if you look at front haul, mid haul, back haul, right? So back haul and mid haul, clearly the latency requirements are very much attainable with the DOCSIS, the HFC that's out there with DOCSIS 3.1. I think so the second part is where it gets more interesting right, where the front haul related requirements have to be catered. So that between the radio unit and the distributed unit, that's all TDM, and there the latency, depending on implementations, could be in microseconds, right? Now, I think Craig had a really good chart which showed the 99th percentile of the round trip delay was less than a millisecond, right? The very last column, right? So if you think about that's RTT. So 1 way latency could be clearly in microseconds in that regard. Now, how practical would that be? I mean, there needs to be some more evaluation that would need to be performed. But for mid-haul and backhaul, it seems pretty practical and logical to take advantage of it, right, Brett?
Yeah, and there is another panel tomorrow talking specifically about using DOCSIS for backhaul and some of the latency aspects that come into play there as well. Jennifer Andrew-Fang at CableLabs has led a project to try to address those requirements, both for front haul and backhaul use cases. And so I encourage you to attend that panel tomorrow.
Yeah, it's basically the elephant in the room question is, many people consider PON to have better latency characteristics than DOCSIS. So with low latency DOCSIS, how does cable latency compare to PON? And does that make DOCSIS better than PON or on par?
Yeah. So thinking of the components of latency, the queuing delay and the media access delay, et cetera, that I had in my chart, PON systems currently have a lower media access delay than DOCSIS does. So in DOCSIS we have these kind of 2 milliseconds and now down to 1 millisecond map intervals. In PON systems, they're in hundreds of microseconds, so they're an order of magnitude shorter than that. And the loop time can also be significantly faster because the OLT is managing a much smaller number of ONUs on a segment. But in terms of that queuing delay, the big bar at the top of the graph, there's really no difference between DOCSIS and PON when it comes to that. That's all the behavior of a network when it's exposed to congestion controlled traffic, TCP traffic and quick traffic. And so that's the same regardless. So far I've not heard PON vendors talking about implementing something like we've done in low latency DOCSIS, but they certainly could. So I'd say today or in the near future when low latency DOCSIS gets rolled out and we bring the latency down to almost deterministic sub 5 millisecond numbers, we'll have better performance than PON. But the PON will catch up. And then that last, low single-digit milliseconds down to hundreds of microseconds. I think realistically for residential usage, that's probably in the noise, honestly.
It leads to the other question that we've kicked around a little bit, and that is, can an off-the-shelf router accomplish the same thing, and why is it better that the operators solve it with DOCSIS?
There are some technologies that can be implemented just in the home router that can do some similar things, to provide separate queues for different traffic. An advantage of doing it in the DOCSIS equipment is that you're much closer to the media, right? So you can implement the things that are very tightly tied to the DOCSIS media acquisition mechanism, and also effectively adapt to when the shared channel gets congested. If you're implementing latency reduction techniques like the FQ coddle and things like that that exist on home routers, they can't really adapt if the shared channel gets congested and provide good latency in those cases. So there definitely are pretty significant advantages to doing it in the modem and CMTS.
Great, cool. Is there any additional questions? Right there in the back with the sports jacket on.
Is it possible for an application to have create service flows of both types, low latency and a classic at the same time?
Yeah, so the identification is on a packet, in the packet header, right? So an application theoretically could create, well, more than theoretically, an application definitely could create multiple flows and have them marked differently. So in the case of an online game, that's the state update packets that are being sent, 60 packets per second. Those definitely mark those non-queue building. If during the course of gameplay, the game needs to download a new asset using TCP, that could just be regular classic traffic that goes on the classic system. Right.
Yep.
Right here up front.
Coming back to the phone question, the question is relevant, but do you think that with your experience implementing in ITU-based phone versus IEEE would be a big difference in terms of implementation?
I don't think there's a fundamental difference there. I'm not a real expert on the nuances between GPON and EPON, but as far as I understand it, the kind of time scales of scheduling are more or less the same between the two.
Yeah. Yep.
And then anything in kind of the queuing behavior and buffering behavior is totally left up to the implementer, I think, in both of those technologies. So it's kind of proprietary as to whether they support any advanced queuing mechanisms.
One question right there.
Yeah, so in the future world, when the modem vendors, the CMTS vendors, and the MSOs are all aligned, what's the business model then for today's gaming service providers? Where do they go in that new world?
Business model for the game service providers?
Right, like today, right, they provide a service that we don't provide today in this company power.
Right.
Once we get there, where do they go?
So you mean if cable MSOs were to start offering their gaming services, where would the over-the-top gaming providers go?
Meaning like today's value they provide because we cannot do what you're talking about today, right? So once we can
okay,
do
so
that, we just go out of the picture altogether, or do they provide something we still cannot provide?
GPNs?
How does that work?
Yeah, well, so the multiple facets, right? So the gaming providers, the most publishers tend to assume there's no coordination, no benefit, no help they're gonna get from the network. So they tend to focus more on adaptive algorithms at the application layer. Right? Now, that only goes so far, right, as I shared earlier, right? So these, as an example, lag compensation algorithms or interpolation algorithms on the client side. Now, once the network in the middle is able to offer better network environment, better behavior with innovations like low latency DOCSIS or with the better optimized peerings, then clearly there is an opportunity to improve the quality of experience. So I think your question would really, the way I'm parsing it is, would the gaming publishers, gaming providers have incentives to come to the MSO for improving their customers as well, experience from the gaming point of view or not? Then answer is yes. If they didn't go there, then there would be other third-party companies such as the WTF that would work from the ISP network peering points to the gaming servers, where there could be multiple ASNs that are spread on the internet, right? To optimize somehow. So that's where the notion of gaming provider gaming private network, GPN, sort of come in to construct something that starts somewhere in the internet, goes up to the internet where the gaming servers might be. And that's usually where the GPNs have a bit of play. Now, there was an announcement earlier this year in which one of the MSOs actually brought that notion of GPN into their network, inside the network, with the notion of giving better SLAs.
Well, on that point of GPNs, so these are applications or services that are intended to optimize game traffic delivery, and WT-Fast is one, Haste is another. We expect them to be early adopters of low latency DOCSIS technology, right? So that's effectively a shim that sits on the PC, the gaming PC, that's identifying the game traffic and then doing something special with it, right? Routing it in a particular way, or sending multiple copies across the network and try to reduce latency. Since that shim is already identifying game traffic, it can mark the traffic as NQB very readily. And so that's a way to kind of jumpstart this packet marking, jumpstart games that can take advantage of low latency DOCSIS by these sorts of applications starting to be early adopters of packet marking.
It's a really good point as well, and I'll make it quick. So there are companies such as Network Next. What they provide is the continuous monitoring of the path between the gaming clients and the gaming servers. And by having their own SDKs inserted in the gamers, in the actual games, and it's a really small library that they insert, and that helps them to monitor the actual gamer's performance on an individual basis, and that allows them to then fine-tune the path as well. Now, they have a way to identify the traffic, as Greg really rightly pointed out. Now, that could be used to add the classification game, whether on the gaming client side at the modem or on the CMTS or beyond, even at the peering points across the network, so having that end-to-end view.
Okay, actually, I thought we had the room, so we were going over, but I'm being given the shepherd's hook, so we can continue these questions outside. Thank you for your participation, your attendance. There's some great questions, and Greg and Rajiv will be available outside for more questions. Thank you.
Thank you.